It's looking like we've got clouds rolling in again here. Next topic for our chapter is some cautions when we're interpreting our correlation coefficients. As I mentioned earlier, that these aren't numbers that are typically very easy to relate to. But because they're pretty much always reported as two-place decimals, people always want to try to relate to them like they're proportions or percentages, which is, of course, very misleading. So, when we're interpreting correlation coefficients, what are some things we need to be thinking about? Something we've talked about before, so as a refresher point, knowing that there is a pattern is not the same thing as knowing what causes the pattern. Simply knowing that things happen in a predictable way doesn't mean you understand why they're happening. So one of the things I said way back in chapter 1 for us is that our ancestors have known for who knows how many tens or hundreds of thousands of years being able to predict the seasons and the path of the sun and the moon in the sky. Doesn't mean they understood what caused those things. Just because we know that two things are connected like height and shoe size does not mean that one of them is causing changes in the other. But people always want to think about correlation as causation. And as I've said to you before, way in the past, it's because we're neurologically wired. We see a pattern and we are pre-wired to assume cause and effect. It's a survival mechanism. So it's something that we have to get control over. We got to pull the reins on that interpretation and go, okay, brain, I know you want me to think cause and effect, but all I can do here is say that I've noticed a pattern. If we want to know cause and effect, we need to run an experiment. We need a t-test or an ANOVA or something. Next thing is a situation we sometimes run into called restricted range. Sometimes you'll hear it called truncation. So truncation, if you're truncating something, you're cutting it off or restricting its range. So if we have a set of data, raw score data, and we cut some of that data out for some reason, we may end up presenting a false picture. So let's think about, we talked about college entrance exams and GPAs, your grade point average in school. So let's say that we are looking at this and we have your, to get into graduate school, a common test is called the GRE. So let's say you've got your GRE scores here and your GPA over here. Well, we would expect a fairly moderate to strong positive linear correlation coefficient for that. So we're going to expect our dots to kind of run in this sort of linear-ish, positive-ish format. That would be fine. But now let's stop to consider if someone did really poorly on the GRE, then they aren't going into the college to take classes and therefore don't have a GPA. We're going to take the people with low GRE scores and we're not going to let them in school. We're going to exclude them. We're going to truncate them from our data. Well, let's just say if we say it's below the middle line. So what this says is we're going to go into our data and restrict some of it. We're going to take all the low scores out. So we're left with just these scores above this mark. Well, look what happens now if we put an envelope around it. It's a 0. That's independence. All of a sudden it looks like there is no relationship between your entrance exams and your grade point averages. Why? Because we've gotten rid of half of the data. So while we did have this nice long string of dots, we now have truncated it. We've restricted it down so that it looks like independence. And so naturally the math answers would change from a nice high positive value to down to close to 0 here. So we just have to be aware that if we're looking at data that maybe range restricted or truncated, that we might be getting presented a false snapshot of what's going on here. So you hear this controversy sometimes when they talk about, do exam scores really predict GPA? The answer in general is yes. Not perfect prediction, right? But in general, yes. Students who score high on that test tend to have pretty high GPAs. Students who bomb don't tend to have very good GPAs. But in studies that show no relationship, most of them have been truncated or restricted. So that's a second thing we have to think about when we're interpreting. Third thing we have to think about is almost the opposite, the issue with outliers. We know outliers are extreme scores, right? So if we get a whole bunch of scores that are showing us independence, that are showing us no real pattern, but we get one or two outliers out there somewhere, right? Extreme scores. That can all of a sudden make it look like a pattern exists, both in a graph and in a number form. So let's think about if I had my data here and that most of my scores were sort of in this kind of range. Give me a nice round envelope that way, right? I look at my envelope and I see that it's pretty round. And I would get a math answer pretty close to 0. No real pattern there. But what happens if I get one outlier? Just one enormous outlier. I get one new score all the way, I'll put them just right over here. Well, what happens? I need to redraw the envelope to include that dot. All of a sudden, we have what looks like a linear positive form because this outlier has stretched the envelope out. We no longer have the little round 0 looking envelope. We had to get rid of it to account for the new data. So we know from other chapters like extreme scores, outliers will mess up a mean pretty good. Outliers can mess up a correlation coefficient pretty good as well. So it's one of those things we have to think about when we're trying to understand what the data is telling us. It's not enough to just know we rejected or failed to reject. We've got to look a little bit more deeply sometimes. And lastly, something I mentioned at the top here, that people want to read these like proportions. If they see that there's an R value of 0.50, let's say, what they want to say is, oh, there's a 50% pattern, or it's 50% good, or it's 50% strong. It's just the terms we're used to thinking in mathematically, culturally. We're used to looking at 2-point decimals and thinking of it as proportions. But remember, they're not proportions. We know that if we want to make this into a proportion, we have to square it, our coefficient of determination. That is a proportion. That is the pattern that is 25% reliable, that allows me to make predictions with 25% accuracy. So you can't just take this base R value and act like it's a proportion, but people who don't know any better absolutely will. So those are 4 considerations when we are trying to interpret and understand our correlation coefficient.